Hello everyone and welcome to our channel, Moo Tekey. A special welcome to all the dairy technologists and students joining us. This is class 5 in our dairy engineering series, where we continue our crucial unit on sanitation by exploring the principles of cleaning, including can and bottle washers, and the fundamentals of clean in place, or CIP systems. In our last class, we covered the hardware, the pipes and fittings. Now we turn to the processes that keep that hardware hygienic. We begin with a fundamental question: why is cleaning so important? We will now look at several images that illustrate the consequences of poor cleaning. The first shows the dirty exterior of a piece of equipment. This is not just an appearance issue. Soil on the outside can easily be transferred to the product. Another image shows a drip tray on an ice cream freezer that was not properly washed. You can see the built-up residue, which is a perfect breeding ground for bacteria. Next, we see a photograph of milk deposits caked inside a centrifugal separator. This heavy soiling severely impacts the machine's efficiency and hygiene. We also have an example of a milk can with a visibly dirty inside surface. This would contaminate any fresh milk added to it. Finally, a milk bottle is shown with visible dirt. This makes it completely unacceptable for packaging. These images lead us to a critical point. Just because something looks clean does not mean it is sanitary. Billions of microorganisms may be present even though they are not visible to the naked eye. This is why both cleaning and sanitizing are absolutely essential in preventing foodborne illness. The substance we are trying to remove is generally called soil, but it has many names like milkstone, deposits, or fouling. In essence, it is simply matter out of place. The effectiveness of washing depends on several factors. These include the nature of the product being washed, the source of the soil, the type of soil itself, the nature of the washing process, the equipment design, and the detergent used. The type of deposit that forms depends on the product being produced, the temperature it was processed at, and the time it was held there. Soils and deposits are typically categorized into 4 main types: carbohydrate, fat or oil, protein, and minerals. A diagram shows how milk deposits form on a heated surface. The layers consist of protein, then minerals, like phosphates and carbonates, and finally, a layer of fat. Effective cleaning requires 4 key parameters, often called the TACT model. These are mechanical force, thermal force, chemical force, and the time these forces act. Imagine these 4 forces working together to overcome the adhesive forces holding the soil onto the surface. Let's explore the 4 factors affecting cleaning in more detail. They are contact time, temperature, chemical concentration, and physical action. A graph shows that the overall effect of cleaning improves as any one of these 4 factors is increased. First, contact time. There must be sufficient time to allow the chemicals to remove the dirt. However, excessive rinsing time should be avoided to save water. The required time depends on the cleaning load, the type of equipment, and other process variables. Next, temperature. A general rule is that a 10 degrees Celsius rise in temperature can double cleaning efficiency. Temperature should be as low as possible, but high enough to permit effective cleaning without using excessive detergent. Very high temperatures can cause new deposits from hard water, which is why an acid rinse is often used to eliminate them. The third factor is detergent concentration. The chemical action and thus the cleaning efficiency is directly related to the composition and concentration of the detergent as well as the design of the system. The fourth factor is physical action. This refers to the force applied to the surface, such as in high turbulent flow systems. Proper pumps and pipeline design are crucial to generating this necessary mechanical energy. Now let's look at the cleaning agents themselves. The main categories are alkaline detergents, acid solutions, detergent additives, and sterilizers, also known as sanitizers. Alkaline detergents include caustic soda or sodium hydroxide, used at concentrations of 0.2 to 2%. Others are washing soda, sodium carbonate monohydrate, sodium bicarbonate, and sodium sulfate. Water glass or sodium silicate is also used for its corrosion prevention and emulsifying properties. Caustic detergents have many advantages. They have excellent detergency when formulated correctly, have disinfection properties when used hot, and are very effective at removing protein soil. Their concentration can be auto-controlled by a conductivity meter, they work well in high soil environments, and are cost-effective. Their disadvantages include being degraded by CO2, being ineffective at removing inorganic scale, having poor rinsability, not being compatible with aluminium, and having their activity affected by water hardness. Acid solutions are used for different purposes. Common types are nitric acid at 0.5% concentration and phosphoric acid at 2%. Acid detergents have the advantage of being effective at removing inorganic scale. They are not degraded by CO2 and are not affected by water hardness. They also lend themselves to automatic control and are effective in low soil environments. They rinse readily. Their disadvantages are that they are less effective at removing organic soil, though new formulations are improving. They have limited effectiveness in high soil environments, pose a high corrosion risk, especially with nitric acid, and carry an environmental risk from phosphate or nitrate discharge. Detergent additives enhance the cleaning process. Sequestrants or chelating agents are materials which can complex metal ions in solution, preventing scale. Examples are EDTA, NTA, gluconates, and phosphonates. Surfactants or wetting agents reduce surface tension, allowing the detergent to reach the metal surface more easily. Finally, we have sterilizers and sanitizers. These include chlorine dioxide, quaternary ammonium compounds, hydrogen peroxide, peroxyacetic acid, hypochlorite, iodophore, and acid anionic sanitizers. The requirements for a good sterilizer are that it must be effective against target organisms and fast-acting. It should have low hazard and low corrosion properties. It must be non-tainting, meaning it doesn't affect the product flavor. It should have no effect on head retention in beverages and have acceptable foam characteristics. Thank you for joining this deep dive into the science of cleaning in the dairy industry. Understanding these principles, the types of soil, the 4 factors of cleaning, and the chemicals involved is the foundation for maintaining impeccable hygiene and producing safe, high-quality dairy products. Author Moo Tekey. Thank you. See you in the next class.